What's up, guys? Welcome to Fun Physics. I'm your host, Edwin Gamez, and we're going to tackle a force problem, specifically an incline problem like this, the infamous incline problem. Ugh. But it doesn't have to be difficult. We just have to take it step by step, looking at everything and just making sure we understand what is actually happening with this problem. So let's get to the question. Reading it slowly. It asks, if m, the mass of our box, is equal to 20 kilograms, and if theta, the angle above the horizontal, the angle of the incline, is equal to 30 degrees, and the mu s, the coefficient of static friction, is equal to 0.670, that between, the box and the actual incline, the surface of the incline, well, what force do we need to just start lifting the box up the incline? Just start lifting the box up the incline. So, looking at that, reading that, well, if we just need the box to start moving up the incline, we don't really need it to speed up. It can move up the incline at a constant speed. V can be constant. If V is constant, that velocity, well, that means there's no acceleration. The box doesn't accelerate. A equals 0. If A equals 0, well, the net force is equal to 0. Because net force is equal to mass times acceleration. And acceleration is 0, well, mass times 0 is 0. Those details are going to help us out, because that just means that we can put a lot of stuff equal to each other. You'll see when we get to that part. Now that we understand that we just need the net force to be 0, we just need that mass to start moving up the incline. Because remember, an acceleration or a net force of 0 doesn't necessarily mean that the object isn't moving. It just means that the object isn't accelerating. Now that we have that information, now that we noted that down, well, it's time to draw our force diagrams. The most critical part of this problem is drawing the actual force diagrams. So if I use this dot as our M, as our box, well, we can draw all the forces acting on it. First things first, we have that pulling force going up the incline. So I'll try my best to make it parallel. That F force, that was a really good arrow. You will not see me do a better arrow than that. But that's our pulling force. We also know that there's gravity. Gravity acting on that box. Gravity is always going down. So we have to make sure that it is going down in this case. Yeah, boy. Well, yeah, boy. Now that force of gravity is going down, well, we also know that there's a normal force acting on the box. Remember that normal force is always perpendicular to the surface. Always perpendicular to the surface. So our normal force has to be perpendicular to this surface of that incline. If so, I am going to draw it as best as I can perpendicular to the incline. Our normal force. Now that's not all. We also know that there's a static friction. Now, how do we know that? We know that just because this force is always changing. Now, we have to know the direction of that static friction. So let me ask you a question. If this force keeps increasing and eventually gets to that point where the box starts moving, well, the box is going to start moving up. That means that its tendency to slide is up the incline. Static friction is always against the tendency to slide, or the tendency to move. So that means static friction has to be going down the incline. Now that we know what direction our static friction is going in, well, there's something else to talk about. If the box is just about to move, just about to hit that point, that means that our static friction has to be at a maximum. It has to be the maximum static friction. Just before it starts moving, it's at a maximum. So we can write that this is our maximum static friction. Now that we have all of those details, well, this is ugly, and I want as many forces to be along either x or along y as possible. So I can pick parallel to the incline as the x-axis, and I can pick perpendicular to the incline as the y-axis. See? I'll pick this axis as x and this axis as y. So I can essentially rotate my force diagram. Essentially rotating my force diagram, well, I have a new diagram that looks like this. Well, it doesn't change. Everything is just rotated. Up y is our Fn. Fn is going up our y-axis. Our pulling force is going to the right on our x-axis because we're rotating this way, going to the right on our x-axis. The maximum static friction is going left along the x-axis, so we can draw that as well. The maximum static friction, max. And we have that force of gravity. That force of gravity is going to be a slant force. So I'm going to try my best to draw it as a slant force. Well, it's going to look something like that. All right? Something like that. We know that when we have a slant force, it is easiest to split it up into its two parts, the x part and the y part. In order to do that, we just have to draw our triangle. And drawing our right, and it has to be a right triangle. We have to draw the right triangle of this diagonal. So to do that, we just draw our right triangle. Boom, see? And now we have to find the direction of those parts, of the x part and of the y part. Because this force is slanted down, our y part is going to be down. It makes sense. Our y part's going to be down. Because if it were slanted up, well, the y part would be going up. It's also slanted to the left. It's also turning to the left like that. So our x part is to the left. So I'm going to replace these with FGY, this vertical part, this y part, and FGX, this horizontal part, this x part. And now we have our new force diagram with everything in a familiar T shape. Now we don't really need to look at this slant force because we split it up into its two parts. It's two perpendicular parts, a y part and an x part. Now everything is in the x and y, along the x and y, so we can get to actually writing our equations. Because this is 2D, well, we're going to look at both parts. We're going to look at our x and we're going to look at our y. But looking at our x, the reason we're going to look at our x is because all the motion is in the x. So, again, we establish that the net force on the box is 0. If the net force on the box is 0 along the x, that means both sides of the x are equal to each other. In order for them to cancel out, they have to cancel out. So, F, this pulling force, has to be equal to this maximum static friction, FFRS max, plus, remember, we also have that part on the x, and this part's also going on that side to the left. So it's plus FGX. Alright? Replacing some of these values, we can do something with it. Now we got F equals, we know that maximum static friction is mu s times the normal force acting on the box. And we know that FGX, when we're talking about inclines, when we're looking at this kind of incline, is mg sine theta. Not mg cosine theta, unfortunately, just because of the way everything is shaped. And I'd recommend that you just memorize that it has to switch in that way. The explanation is you can understand the explanation, but I find it easier to just memorize the idea. But I can tell you the reason it is. The reason that this is mg sine theta is because this angle right here is not theta. It's not theta. It's actually 90 minus theta. The reason that's 90 minus theta is because, well, this triangle, if I were to lower this down, well, this right triangle has to equal 180 degrees. We know that this is 90 degrees. So that means that this angle plus this angle have to equal 90 degrees. Theta plus 90 minus theta, well, that'll equal 90 degrees. That's how we know that this angle is the complement of this angle. The complement, or in other words, 90 minus this angle. So we can say, so knowing this angle actually, well, we can just say that the FG in the x direction is, writing it down up here in this corner, well, it's just mg cosine because it's adjacent to this angle, cosine, but not of theta, of 90 minus theta. And the cosine of the complement of this 90 minus theta is equal to sine of theta. And that is pretty much the explanation for, a general explanation for why the trig functions switch. Going back to the problem though, crud, we don't know what normal force is. We don't have something that we know. Remember that to solve an equation, we just want one unknown. We know mu s, we know m, we know g, we know sine theta, but we don't know the normal force. So we got to look at y. We got to look at y in order to get an idea of what normal force is. So let's look at y. Once again, the acceleration in the y direction is 0. The box doesn't move up above the incline and doesn't move into the incline. So we can just say that both sides are equal. Up is equal to down. Fn, the only force going up, is equal to Fgy, the only force going down the y. And we know, because Fgx is mg sine theta, Fgy must be mg cosine theta. And now we actually have a value for Fn. So plugging it back in to our original equation, well, we can plug that back in. And now we have that the force is equal to mu s times mg cosine theta, that normal force, plus mg sine theta. Now we know all of these, and we're solving for f. We're directly solving for f, so we can just plug in all of our numbers now. All of our numbers. So now f equals the mu s, which we said was 0.670, times the mass of the box, 20 kilograms, times g, I'm going to use 10 in this case. You can use 9.8, but it'll give you an answer around the answer that I'm going to get. They're both completely correct, though, in terms of, like, on a test, in the context of a test or quiz. Cosine theta times cosine theta, the angle is 30, plus, once again, the mass times g, which is 10, times sine theta, sine 30. So, plugging everything in and doing all the multiplication and addition, well, simplifying everything, we get a final answer for that minimum force that we need to lift up the box. And that answer would be, plugging it into my calculator, actually I did this before, the whole answer would be 216 newtons, about that much. Now, depending on if you use 10 or 9.8, you might get an answer slightly lower, I believe. But they're both correct as long as they're around this answer, as long as your steps are also correct. I hope that helped, but let me recap all that we did. We recognize that we just need the velocity of the mass to be constant. We just need the mass to go up at a constant velocity. Doesn't necessarily say that it has to accelerate. So that means our acceleration can be 0, and that our F net on the box can equal 0. The net force on the box can equal 0. And because of that, well, after doing that, we drew our force diagrams, the critical part. We made sure to draw all the forces as they are acting on the box, and then we rotated it so that as many of our forces could be perpendicular, or could be in the y or in the x. And usually that's what you're gonna do on most incline problems, is that you're gonna make this the x-axis and this the y-axis. Parallel to the incline is gonna be your x. Perpendicular to your incline is gonna be the y. Doing that, we found that our FG is now a slant force, so we had to split it up into two components by making that right triangle. FGY goes down, FGX goes to the left. And now that we had everything either in the x direction or in the y direction, well, we could actually make our net force equations. Knowing that F net equals 0, both sides have to be the same, both sides of x have to be the same, so F has to equal the maximum static friction plus the FGX. And remember, we said that we're looking at the maximum static friction because we're looking at the point where it's just about to move, just about to pass that maximum value for static friction. And doing that, well, we found that we needed normal force, so we had to look in the y. Acceleration along the y is also 0, so we could say that both sides are equal. Fn has to equal Fgy. Both have to equal each other in order to cancel out. So Fn equals Fgy, it equals mg cosine theta. We just plug that value back in for Fn. And doing that, well, we had just one unknown, our force. We plugged in all of our numbers, and at the end we found that the force needed was 216 newtons. So I hope that helps. That it could definitely be a type of problem that shows up on a test or examination, but yeah, I just wanted to play around with my whiteboard. But seriously, I do hope it helps, and I do hope I could give a slow enough guide or an understandable guide to how to solve this problem step by step. Thank you.